Hello and welcome to this webcast on Geographic Calculator. I'm Katrina Schweikert, an application specialist at Blue Marble Geographics, and I'm here with Sam Knight, the Director of Product Management.
Hello everyone, and welcome to today's session. Today's session is going to be focusing on Geographic Calculator 2015, Service Pack 1. We're going to be focusing on a system called Horizontal Time Dependent Positioning. This is going to also add the time component into our spatial coordinates. So we're going to be looking at potentially latitudes, longitudes, elevations, northings, eastings, elevations, all the typical spatial components of our data, but we're also going to add in the temporal component. So not just where your data is, but when your data is. We're going to be looking at a system called Horizontal Time Dependent Positioning that is a toolkit published by the U.S. National Geodetic Survey that we've embedded in the Geographic Calculator for several years now. We're going to be looking at a few key dialogues and interfaces in the Geographic Calculator. We'll look at exactly how HTDP is enabled on the GeoCalc dialogues, where we work with our coordinate systems, making selections, defining new systems. And then we'll put those to work on the interactive conversions job, the point database conversions job, and vector data conversions job. Most of our examples will focus on the interactive conversions job, since these are just a simple component of the coordinate systems themselves.
You can subscribe to these videos from our webinars page at bluebarblegeo.com or from our YouTube channel page. Additionally, you can find out about training opportunities on our training site. Both web addresses are shown on the screen and are linked from our homepage. To get started, Sam, where exactly is HTDP used?
Okay, so HTDP, I mentioned, is a product of the National Geodetic Survey here in the U.S. They work collaboratively with the similar Canadian authority and the similar Mexican authority. So the systems we're going to talk about that are HTDP enabled is how we refer to them here. Those systems are enabled for all of North America. So that goes all the way up into northern Canada, out to Alaska, and then down to the southern reaches of Mexico. There are a couple other systems we're going to be just sort of mentioning, and we're going to skirt around them. There's another kind of temporal shift we have called a 14-parameter transformation. And those types of transformations apply anywhere on the world. There's some of them in Australia, some are starting to come online in Europe, but today's session is mostly going to focus specifically on the HTDP tools. I have a couple of images up on screen, and you'll see there are different representations of velocities of tectonic motion, and these are specifically within the continental US, but these models extend up through Canada and down into Mexico as well. You'll see that the western half of the US and the eastern half of the US are broken into two different models for showing the velocities, because they have drastically different magnitudes. The scale bars towards the bottom of the screen show the very drastic difference in velocities, particularly along the Pacific coast in California. You'll notice that some of those shifts are up to 50 millimeters a year. So we're talking about several inches a year, whereas on the eastern half of the country we have much, much smaller velocities. The plates are moving around a lot slower. Down towards the southern end of the country, down in Texas and Florida and parts of the central south, those are slower velocities, just down around a millimeter to a millimeter and a half per year. And then as we go north, as we go west, and as we go east, we see increased velocities. So up where we are in Maine, you'll see that we're moving at about 2.5 to 3 millimeters per year. It doesn't sound like much, but when you factor in how long we've been doing this very, very highly precise modeling, we can actually transform our coordinates to fairly significant distances when we start compounding those shifts over the years. So when we started our very sort of highly precise surveying techniques, and let's just generalize to the early 80s, when GPS started really seeing common use in surveying, we started being able to show this drift over the years. And now, we're 30 years later than that. And we've been adding these few millimeters a year until some parts of the country, and particularly in Western California, you'll see shifts from the early 80s that are sometimes on the order of over 4 meters in shift. So when you think about highly precise positioning, if you drive a survey pin in the ground and record its coordinates relative to the reference frames at use in the early 1980s, and then we leave that for 30 years and we come back later, when it's moving several inches a year, that's going to total up to a rather significant and measurable amount. And that's the entire point of this survey tool provided by the NGS called Horizontal Time Dependent Positioning. This helps us model the tectonic motion against all of the common reference frames that we do our mapping with all throughout North America.
Can you remind us which jobs in the calculator can use HTDP?
Okay, so HTDP is not enabled everywhere, and this is specifically HTDP and the other 14 parameter transformations we've mentioned. They're going to be found on the interactive conversion, where we're talking about converting one single coordinate between coordinate systems or reference frames. This is going to be also on the point database conversion, where we're talking about spreadsheets of numeric data. So in this case, we've got a spreadsheet, an Excel sheet of northings and eastings in a UTM projected system, projecting coordinates en masse from one set of columns to another column. And as well, we're going to find this on the vector data conversions job. So here we're going to be converting things like shape files, map info tab files, AutoCAD formats, LiDAR formats, and so on. You'll notice each of these has the date boxes enabled on the coordinate system controls. Whenever we see the date boxes, that's where we're going to be able to use HTDP.
And is HTDP enabled for all coordinate systems?
HTDP is not actually enabled for all coordinate systems. There's a very small subset of the coordinate systems that are used here in North America that these apply to. And at the same time, it's not all of North American systems. So on screen, I have our usual example point going from NAD 27 to NAD 83 in a projected coordinate system. So NAD 83 on UTM zone 19. So NAD 83 is actually HTDP capable. NAD 27 is not. So let's take a look at the differences there. I'm just going to right click on my NAD 27 coordinate system. I'm going to open up its information. On the identification panel, we see all the usual information, all of the identifiers, the remarks from the EPSG, and we see its definition. Now the place to look for HTDP capability is on the notes of the datum itself. So we're going to open up the datum, North American datum of 1927, and take a look at its information. In the identifiers, you'll notice that there are a number of identifiers there, but one of them is not HTDP. HTDP capable systems all have their own identifier, and it is coded into the HTDP system that is published by the NGS. So that's a toolkit that we've embedded into the calculator, and we call each of these systems by a coded entry that puts it in the context of the HTDP toolkit. So NAD 27 does not have that capability here. I'm going to go over to the projected coordinate system side, and we're going to crack down into its definition. So I'm going to open up the base geodetic definition of our UTM zone here. So this is giving us the geodetic coordinate system of NAD 83, and now I'm going to open up the parameters of its base datum. In that base datum of NAD 83, you'll notice an HTTP issuer code in the identifiers list, and the authority code is NAD 83 underscore 1986. And that keys it into the initial reference frame of the NAD 83 system from the early 1980s. All of the HTTP systems, to make this a little bit simpler to recognize which ones are HTTP capable, we've also grouped those into their own folder in the GeoCalc dialogues. So under the data source menu, we can go down under coordinate system definitions, and if we take a look in the geodetic folder, you'll notice there is an HTTP folder. This contains all of the HTTP capable systems that are used in North America. Now this is a mixture of systems that are worldwide systems. If you notice the area of use column, many of these are actually worldwide systems, such as all the ITRFs. That stands for International Terrestrial Reference Frame. Those are used all over the planet by many, many different countries. There are a couple of North America specific systems in there, mainly the NAD 83 based ones. Some of those do extend beyond the typical North American bounds, stretching across the Pacific. but many of these are worldwide systems that have transformations that are localized through the HTTP system. So even though these are international systems, they do have special capabilities when being transformed here in North America. Now, to actually work with these on a job, I have a couple of interactive conversions already set up where we can take a look at the capabilities of these particular systems and their specialized transformations. So here on our normal sort of non-epic specific transformations going from NAD27 to NAD83, the key choice on most of these jobs comes down to selection of the coordinate transformation linking the input system to the output system. Now if we double click on our coordinate transformation box, we're going to get our usual horizontal transformation picker. And we'll see all the usual categories over here on the right. We have our data source transformations that give us things like datum shifts, and we have generated transformations that sometimes link multiple transformations back to back to give us what we refer to as a fixed epoch transformation, meaning the dates don't matter in this context. So these are for non-temporally related transformations. So I'm going to back out of this and I'm going to hop into one of our HTTP jobs that I've got set up already. So this is a transformation from NAD83 over to the current epoch of the WGS84 system known as G1674. This is the reference frame that is considered coincident with the ITRF 2008, the International Terrestrial Reference Frame 2008. Those are considered to be coincident. And we can take a look at transformations for this. When we double-click the coordinate transformation box, we're going to see a new category of transformations light up in the categories on the left. And for this specific combination, you'll notice that only time-dependent transformations show up. These are indicated in bright blue as if they were a custom datum, and we do that specifically because the parameters for these come from an external kit. So these are calculated by the HTTP toolkit, and they're calculated on the fly based on the input dates of those coordinate systems. So there's not really any parameters that we can look at for these. We can open those and view the transformation just like we can for any other system, but all we have is the source epoch and target epoch, and those are referenced in decimal years. So that is a base 10 fraction of the day of the year for the date that you've entered in. So in this case, I had a date saved in there from back midway through 2011. You'll notice the method also says it is referring to the HTTP converter. So that is going into the NGS kit. We hand the coordinates over. They are run through that software, and they are converted back over to us. And we do that for any of those types of data that we're going to be looking at here in the calculator. Once we have our transformation selected, you'll see it is going from our input datum of NAD83 to our output datum of WGS84, G1674, and it lists for us both of the epoch dates for input and output. Now, in this job I already had saved was the same epoch. And there are cases here where we might do this on the same epoch, and there are cases where we might do this transforming between epochs. That is one key differentiator here between the HTTP type transformations and the 14 parameter transformations we'll take a quick look at later. HTTP is actually able to do several things at once. So it does temporal shifts between these reference frames, but it will also do a fixed transformation between these. So there will be three things going on depending on the combination of reference frames and epoch dates that we put in. If we're going from two different reference frames to two different epoch dates, it will actually be doing three different things under the hood before it returns your coordinates. Two temporal shifts and one spatial shift. So the combination we have here, NAD83 to WGS84 G1674, if we apply these on the same epoch date, and so let's just go ahead and do this relative to today. So I'm going to click on my date picker and click on the year to get us up to 2015, and I'll just put in today's date. It is September 15th today, and same thing on the output side. When we go to pick our coordinate transformation, we'll see the one and only temporal transformation. The WGS84 reference frames that have the G codes associated with them are specifically only able to be transformed right now using the HTDP tool. So that is why it is the only one that shows up. And we can calculate out our final conversion. Okay, so now that we've completed our conversion, that was a nice simple one where we only had an HTDP option for transformation. So what happens when it's a little bit more complicated in our coordinate systems and we have more options to pick from? A good example of that is a transformation between one of the NAD83s and WGS84 Transit, or the original WGS84. I'm just going to double click to select a slightly different coordinate system, and I'm going to grab WGS84. So this is the WGS84 most of us are talking about when we are working with other spatial packages. It's the one that is assigned to an EPSG code of 4326, so it's sort of our plain vanilla WGS84, if you will. And you'll notice that when I select that alternate coordinate system, the coordinate transformation box clears out just like it usually does whenever I change coordinate systems. The same is true of HTTP, just like any fixed epoch transformation. When we go to pick that transformation again, we just do the same thing. We double click. And this time we'll see we have a list of all of the different ways that we can get between those two. So in this case we have a number of generated transformations that are combinations of individual transformations to get from NAD83 to WGS84, stopping on a few different systems in between. We have single transformations like we would normally expect to get from the source to the target system, and we also have our time-dependent transformations. Now, if we're specifically looking for the time-dependent transformation, it's going to be fairly easy to recognize. It's going to be in bright blue. That could also, other systems could also show up in bright blue if you have custom transformations derived. But if you want to isolate those, you can just click on time-dependent transformations, and you'll see only those that are actually doing a temporal shift. The same is going to be true when we see a 14-parameter shift selected and available as well. So I can grab onto my HTTP-based shift, click OK, and go ahead and finish off my final calculation. Now you'll notice here that the same coordinate for start and output in our conversion has been calculated. Some of these HTTP-based systems are coincident with each other, such as the original NAD83, sometimes referred to as NAD83 1986, and WGS84 Transit, more commonly known as just simply WGS84. So this is part of the confusion for a lot of folks, why people will say that NAD83 and WGS84 are the same thing, because functionally, way back, they once were. So they are coincident reference frames. If you put in a similar epoch date for each of those, you will actually calculate the same coordinates for input and output. It's when you start picking the alternate realizations of those systems. So you start picking things like WGS84 with any of the G codes, like 873, 730, G1150, or G1674. You'll start noticing some of those shifts in the reference frames show up. If we select a different date for these, let's take our output system and we'll go way back. Let's go back to WGS84. Let's put that back in the early 1980s. So let's go back right around the GPS 0 day. So we'll go back to January 1st, 1980. So somewhere along where GPS was actually turned on. If we do the same thing and calculate our transformation between those two epoch frames, you'll notice there's only a slight bit of shift, a much smaller shift than we have when going between the G1674 reference frame. So there is some shift that comes along in those relative to the epoch dates, even if they are coincident. But the larger shift is where we're going between the older frames to an older epoch date to a modern reference frame with a current epoch date. That's where we start realizing those 4.5 meter shifts that we have out in California and up in the Canadian regions up towards Alaska and things like that. So some of the differences we'll see there in between those reference frames.
Okay, so how do we turn this on if we don't see the date controls?
All right, so some users won't actually have the date controls. And that could be for a few reasons. First of all, single user installations will have full control over this. And if you're on a network, it might be a little bit different for you. So there's two different paths we're going to go down. There is a preference setting that toggles on and off whether or not you have time-dependent transformations enabled. So we're going to look for that under the Options menu and specifically in the Preferences dialogues. So on the General tab of the Preferences, there is a setting right in the middle for Enable Time-Dependent or Epoch-Based Transformations. If you don't see the date boxes at all in your workspace, you've probably got that toggled off. If we toggle that off, we'll see my interface changes to get rid of the dates. You will never be able to select a 14 parameter or an HTTP enabled transformation. To turn that back on, you just go back to the same place and we toggle on time-dependent transformations. And here's where it gets a little different if you're a single user or a dongle user or if you're a network-based user. I'm just going to toggle mine back on and let's talk about some of those differences. So if you're a single user and you are the admin of your own system, you are going to have permissions to toggle that on or off at any time. So if you want to turn that on, all you have to do is go to the Preferences menu and flip the switch and you should be good to go. If you are on a network site license or something like that where you have an administrator that is a local administrator responsible for setting up your starting workspace, you may or may not have permissions to make that change in the preferences. That is something that is controlled by the administrative settings, and so if you are not able to make that update in the general preferences, you're going to need to talk to your network administrator to find out about getting permissions if you're supposed to be able to do that in your installation of Calculator. If you don't know who your network administrator is, send in a note to our tech support group here, geohelp@bluemarblegeo.com, because we do know who your administrator is, and we can get you set up with what you need to know about getting that turned on. If you do have the permissions as a network user, or even if you're in a network-based license setup at your company, and you have a rare admin locked single user installation, the same thing applies. You're going to need to work with your network administrator to get the workspace password to give yourself the permissions to unlock those settings. But that's where you turn that on. And for those of you who are viewing this for use in other parts of the world, the 14 parameter transformations are controlled exactly the same way.
So what about everybody else?
Okay, so for those international users we've been mentioning, for parts of the world such as Australia, we have another job set up here, and we're going to take a look at a similar transformation. So here we have a transformation with a point down in Australia of ITRF 2000, one of the common GPS era reference frames, and GDA 94. The Geodetic Datum of Australia from 1994. That's essentially Australia's version of the same thing we have here in the States, our National Reference System, NAT 83. So ITRF 2000 to GDA 94. We have a number of Helmert transformations, that is a 14 parameter Helmert transformation to transform between the various ITRFs and GDA 94 epochs, and those are all provided by the Australian government. For this particular coordinate that we have, this is somewhere squarely in the middle of Australia. When we go to make our datum transformation, you'll see a time-dependent transformation comes up, and that transformation is indicated in black text with the padlock icon indicating that this is a stock definition. This one is actually parameter-based. So if we pop that open and view its transformation, we'll see that we can get into the parameters of a 14 parameter time-dependent Helmert. So one of our longer transformation names. And there are 14 parameters listed in there. Those 14 parameters are what is commonly known as a 7 parameter transformation, where we have a shift in the X, Y, and Z Cartesian axes, a rotation around the X, Y, and Z Cartesian axis, and then also a scale from that reference frame. The remaining 7 parameters are the velocities of change of each of those parameters based on what year it is. So you'll notice all of the rate of change along with the translations, the scales, and the rotations themselves. So those are fixed parameters that adapt themselves based on the dates we put in. So I'm going to back out of these a couple of steps. We'll see that shows up as an ITRF 2000 to GDA 94 time-dependent transformation. And those are based on the epoch date that we put in for input and output. Now, one requirement here of the 14 parameter transformation is that you have to have the same epoch date on both the input and the output. That is a slight limitation compared to the HTTP-based transformations, and that's simply because there is one transformation taking place in here. So it has to be in the same frame at a common epoch to be able to come up. If we change those dates to anything else, I'm just going to quick grab a random date in the past here. When we go to make that transformation, you'll get an error message that says we are unable to find a transformation between the selected coordinate systems, just as if there was no transformation at all. So a key piece of this is if you are doing those epoch-based transformations, you do need to have the same dates on both sides. So I'm just going to quickly put our date back to the original date that we had. So we had July 20th on both sides there. And now we can select that time-dependent transformation to go between those two reference frames at that same epoch date, and we can actually go ahead and calculate the output point again. So that's the slight difference in the 14 parameter transformations and the HTTP-based transformations. So I mentioned that both of those transformation types were supported on multiple jobs. So on the point database conversions job, just as if we were setting up a normal point database conversions, we set the dates and the transformations are going to be selected in the center exactly the same as they are on the interactive conversions job. The vector data job has this capability as well. You'll see those date boxes. Essentially any job on which you see those date boxes, you're able to do the time shift. Now presently we don't have that capability on the raster transformation job, or rather we hadn't had that capability on the raster transformation job up until the service pack of 2015 this year. We do also support those transformations against raster database jobs now. The key thing that some folks often miss on those is the spatial resolution of your raster imagery has to be fairly fine before you'll see a noticeable shift in the pixels. If you're working with imagery at the 1 meter level, it's actually hard to visualize those transformations because of the pixels themselves taking up a fairly large area. Unless you're in a part of the world that is seeing shifts of several meters of those pixels, it's a little bit harder to notice on those raster image-based files. Where we have the numeric coordinates, so on interactive, on point database, the seismic survey job, and the vector data job, all of those time-based transformations are a little bit easier to visualize, and they take place just like a normal fixed epoch transformation.
So is there anything special someone should be aware of when sharing this data?
Yeah, so the trick with doing these time-based transformations is that they very often apply to surveyors. Surveyors are probably the ones that are most focused on these types of shifts, and they're working very commonly with individual control points, point databases, very small point databases of things like property bounds. But these do have much larger ramifications for everyone when we start talking about fairly regular map data, when we start talking about these shifts that are up into the 4 meter range. That's a notice that it's a difference that everyone can notice, even at the slightly less accurate, what we refer to as mapping grade accuracy, where we're not interested in those sub-meter positions. It's getting increasingly common for everyone, and so there are some concerns when passing this data around. The first of which is many of the file formats that are involved don't have any way to actually accommodate the epoch that the data was recorded on. So that has to be recorded in some other means. There are increasingly starting to be reference formats that will actually store these. Some of the datum names are starting to be recorded in various software systems, but on large part there is no clear standard for a way to include an epoch date with most regular data. Therefore, it is fairly critical, if you are really working with this high precision data, to maintain that in the metadata files that go along with the spatial data you're delivering. Really, the end user is the one that's responsible for clearly communicating that. And so if you are working with high precision data, you need to be aware that you will lose that precision when handing it between users if you are not properly also recording that epoch date somehow that is clear to the person that's actually receiving the data from yourself. When you're requesting data of people, if you don't have the epoch date that's associated with when that data was created, or the data that your data was created from, if you're dealing with things like secondary data, then it really is up to you to make sure that you have that when you get your data. Otherwise, you're not going to be able to confidently apply these very subtle transformations. So along with the requirement for high accuracy transformation, also comes the requirement for high accuracy metadata and very specific metadata. That's really the largest thing, is there's no clear standard way to apply those, and it's an evolving part of the technology right now. It is a fairly interesting time as more of these time-based transformations are coming online around the world. It wasn't too many years ago where HTTP was really the only simple way to do these transformations, and it does only apply to North America. Since the Australians have come online with the 14 parameter transformations, and we've started seeing some for different parts of the world. Very commonly, it's the places in the world that are a little more seismically active, where we've had large earthquake events take place. Japan has started to put together these time-based models really all over the world. In different countries in Europe, there's a lot of collaboration on this front. But it is an evolving part of the industry, so there's a lot of interesting stuff happening right now. Okay, so that's about going to do it for all the content we have in today's session. If you have any questions about anything we've talked about or other things that you'd like to see in upcoming web sessions, please feel free to send those questions in to geohelp@bluemarblegeo.com. Visit us at our homepage at bluemarblegeo.com. So thank you everyone for attending today, and thank you Katrina for joining me.
Thanks, Sam.
And we'll see you next time.